Well, hello once again. This is the next in a series of recordings on what amounts to the improve phase activities of the Six Sigma team. In the previous videos, we introduced the idea of design of experiments, specifically showed how to use the custom design platform in JMP to design an experiment. And now what we're going to do is look at the results and the analysis of the results from the actual experiment. You really should have read the notes, the Chapter 6 Part 3 notes from pages 10 through 37 before viewing the video. I'll review some of it, but not all of it. And I would point out that there's an interesting challenge to this experiment in that there are 4 responses. We have targets and specification limits for each of the 4. So this is what we call multiple response optimization in JMP. Again, this is not a complete DOE course. What we will do is show the basic concepts of how we deal with these multiple responses and show you that JMP is an extremely powerful tool to actually deal with the problem of simultaneously trying to optimize a set of responses based upon a model that we fit and based upon the inputs to the process. Okay, there we go. Okay. So when we do optimization, we basically think of it today in what is often referred to as desirability. Meaning we'd like to find settings of the input factors, then using our statistical models, come up with a response level that is in somehow most desirable. And desirable can typically be thought of in terms of, and I'm going to skip through some of these details, they're not necessary. Some of the mathematical details, you have the notes to read. But as I was saying, there are basically 3 things you think about. Maximizing, in other words, bigger is better. So if you're trying to maximize, desirability, in other words, has a value of 0 for the least desirable and 1 for the most. So using your model, you would search through a grid of settings for your 5 factors that would give you the most desirable response. And rather than use the original response itself, we convert, and some people would say transform the response to this desirability scale. It's dimensionless and it goes from 0 to 1. So if you want to maximize, basically what you're trying to do is find settings that will give you the highest response. In other words, maximize. Similarly, if you want to minimize, then the high response would be least desirable as 0, and the highest response, then the lowest response, a 1, for the most desirable. So just the opposite. And then finally, JMP does a nice job of what we call match a target. And this is what applies in our example. So if we can find settings of the factors that let us hit the target for each of the 4 responses, then that's a 1. In other words, we found the most desirable settings of the factors. And now we can't always exactly hit the target, but quite often we can find settings that will allow us in combination to hit them. So we call those desirability functions. Again, you can read, if you'd like to, the mathematical details. I don't think it is really necessary to go into all the detail. The use of them is obvious. And in JMP, since we are fitting statistical models, we use the platform with the obvious name, Fit Model in JMP. It's powerful and very flexible, and I'm basically going to go to the results and actually talk you through the analysis. But if you look through the notes, you'll find there's quite a bit of information in here, so I do encourage you to read through the notes. Okay, so at this point, I'm going to go over to JMP. And this is the 12-run experiment that was created in custom design, and these are the 4 responses. And remember, there are specifications and targets for each of the responses. These have actually been stored in the column info window for each factor. So I'm going to highlight thickness as an example. Right click, go to the column info window, and notice under column properties there are specification limits. So for thickness, it's 0.9 microns plus or minus 0.2. We also have what are called response limits. The difference is spec limits are for estimating quality performance. Response limits are actually for the optimization. They appear redundant, but they actually serve 2 different roles in how they're used. Well, similarly, we've done this for the other 4 responses. So we've stored these spec limits and response limits as column properties, which basically saves us a lot of time down the road. Okay, so they're all saved. And also, something else we want to do is for some of these factors, I'm going to just illustrate this to you. I'm going to go to the column info window for Anodize temp. Notice there's a column property called sigma, and there's a value of 1.5. What this is, they know in actual practice, when they run this process, they cannot hold the anodized temperature constant, and through measurements taken on the process, they found the standard deviation of temperature to be about 1.54 degrees. So later I'm going to use this information, and you'll see why, but for most of these variables, through observational data, I have stored a value for the standard deviation. Basically what this is an acknowledgement of is, even though I control these factors in an experiment, in the actual process I may not be able to. So how do we go about analyzing the data? Well, first I want to fit a model, and remember I showed you in custom design, when you save the design it saves the model. So I'm going to right click on model and select run. This opens up the fit model window, or if you want to do it manually, fit model is in the analyze window. This is a very intelligent and very easy to use platform. It does many things, many of which are really beyond our scope. More advanced features we really don't need. So notice it put in our model, our main effects, and our 4 potential two-way interactions, and it put in all 4 responses. However, when you have multiple responses, what you should first do is analyze each individually. So I'm actually going to remove the other 2. We'll fit those individually, and this will be set automatically for you. Emphasis just gives you a default setting that's very nice for design of experiments. So we're going to run the model. Okay. Notice at the top, this is for thickness, and JMP gives you a breakdown of the effects and their relative magnitudes. To the right, you see something called a p-value, which is basically a measure of the size of the effect. A small p-value typically means a big effect, and JMP has something it calls a log worth, which is just really the negative of the natural log of a p-value. Just they think it looks more intuitive. So we look through this, and what do we find? That all of the big effects are anodized temp, time, and acid concentration and interactions. So it looks like most of the anodized terms in the model, the anodized tank terms, are important, with some exceptions. Notice there's no anodized temp by time interaction, And then notice all the dye tank factors have very big p-values, meaning they have a very small effect. This is important because remember, the dye tank cannot impact thickness. So it's important that in our analysis we're able to show the dye tank is not having a big effect. So basically, what effects do you pick? Well, notice JMP draws in this blue line for you. Basically, things that touch the blue line or exceed it should be considered important in the model. The farther they are below it, the more likely you are to remove them. One important rule. Notice the variable acid concentration. Its effect is pretty small, but notice it's involved in interactions that have a large effect. So if you have a variable, a main effect that's involved in interactions, you always leave it in the model. And if we look down below in what's called the parameter estimates table, typically, and I don't necessarily think this should be used as a rigid rule, JMP highlights all of the terms that have a small p-value, which roughly means have bigger effects. So the p-value is controversial, but typically a cutoff of about 0.05 is used. Anything at 0.05 or lower is considered a big effect. Anything above that basically is considered not an important effect. It's somewhat arbitrary, but that's a common rule. So JMP is showing what it considers to be the important effects. What we can do is go through this and remove some of those effects that are relatively small. So I'm going to actually remove 4 of the effects. So I go to my effects summary, hit remove, and they're taken out of the model. Okay. So this is my final model. And again, what's important in this model is that nowhere does the dye tank factor show up, or we'd have looked rather silly because the dye cannot influence thickness. Once we have done this, and you'll see why later, go to the main report menu, go to Save Columns, and save the prediction formula. Okay? And when you do this, it literally saves the formula to the data table and shows you the predicted thicknesses. This is important because these prediction formulas form the basis for optimization. So I'm actually going to remove that formula I just put there. You'll see why in a moment. And notice we have fit models for all of the responses using exactly the same methodology I just showed you. So notice this is the L-star model, and these are the terms that went into it. In fact, what you'll find is every one of these responses had a different model. In other words, different factors had a big effect on each of these responses. So when I'm done, I saved a little script called prediction formulas, but in general I would go through, fit a model to each response, and then save the formula to the data table. So I'm going to go ahead and save them. Okay, so I'm going to run the script. So there are my prediction formulas. Okay. Now why is this important? Well, it turns out that once I have these formulas saved, I can then go and do optimization as I described earlier. And optimization in JMP is done through a wonderful tool called the profiler. Okay. So I can run the profiler in fit model for each response, and I'll just illustrate that for you very quickly. So I'll go back and run the thickness model. Okay. So this model contains all the effects that seem to impact thickness. And then down the bottom you see what's called the profiler, What the profiler is, it's a dynamic visualization of the model. So many people will look at these essentially regression models for the response, and they have trouble understanding them. Well, using the profiler, you can simply move the cursor around, that would be the horizontal line, and I'm changing the settings of the factors, okay? And what happens to the left, it tells you the predicted response. Okay? So basically, and by the way, as I move, for instance, acid concentration around, notice how the slope of the lines for temp and time are changing. These are interactions. The slope of the line basically gives you an idea of how that factor impacts the response. Okay. So if I'm at high acid concentration, both anodized time and anodized temperature have a positive impact on the response. Okay. If I go to low, notice at low concentration, time has little effect, temperature has a big effect. Okay. Or if I wanted to, I could notice also if I start moving around some of the other factors, the slope of acid concentration changes. And that's because of interactions. And also notice that there is a desirability function that's already showing, and you'll recognize this as wanting to match a target. So what you do is you click on the menu for the prediction profiler, and there's an option to maximize desirability. It does a brute force search for settings of the three factors, the anodized factors, using the model to find the settings that give you a target. Okay. And by the way, they found about 83 degrees for anodize, temp 30 minutes for time, and about 170, and I've forgotten what that's in for acid concentration. And by the way, there are actually many other solutions because I'm just trying to match a target. Well, I don't want to do that individually. I want to do that for all of the responses at the same time. So I fit a different model to each of my responses. Okay, and then after I did that, I saved the prediction formula. So each column actually has the model stored in it. So now, right from the data table, I go to the graph menu and I open up the profiler, since it's a graphical display, and I just take my four formulas and put them in the prediction formula window. So notice the desirability functions appear for each of the responses. If they do not appear, you haven't set them in the column. In the report menu for the profiler, you can actually set them manually using desirability. Now what do? I want to find settings that will let me simultaneously hit all the targets. Here's a bit of a problem. Let's look at anodized temperature. Notice it has a positive effect on B star, a negative effect on A star, a negative effect on L star, and a positive effect on thickness. So what we have are actually competing relationships. So what I've got to try to do is find settings that more or less balance these positive and negative relationships and let me hit the target. So I simply go to the prediction profiler menu and select, and I'm going to use maximize and remember. So what this is doing is quite comprehensive. It went through and found settings that came as close as possible to hitting all the targets. Notice every one of the targets is well within the specification limits. So it looks like if I run at these settings, it's predicting I should have acceptable parts. Okay, so this is kind of an important result. So basically what I've done, I have fit a statistical model containing the important terms for each of the responses. I saved the prediction formula to the data table. Then I picked the profiler from the graph menu, and then using the desirability functions in the profiler, I found optimized settings of the input factors that let me hit all of the targets. Okay, so at this point we're going to end this recording, and then we're going to talk about some further analysis that was done on the capability of this process.